Can you see the slide deck?
Yeah.
Okay. So quick background. This picture probably, it might look familiar. This is how things look. This is what we were supposed to have May 13th through 15th. And this was going to be in Tucson. So that's like a 230-meter runway. It's an RC runway, not for full-scale airplanes, but still very big. You can see kind of the shape structures here. And since the event was not going to happen as a result of the pandemic, I feel our new plan of kind of going to space using this opportunity to, no pun intended on the rover name, but using this opportunity to load some terrains. I know Darwin is working on some planetary surface related project threads. Is that correct, Darwin, with Andrew?
Yeah, not more just navigating. And
yeah, but like, the domain, it's all about domain. Like, all of these domains are in some sense a long history, right? But like in our school at ASU, we have a bunch of faculty actually, including Dr. Jim Bell, who routinely develops equipment for, rovers, at least Curiosity and Mars 2020 has instrumentation from their group. So I think it's a good fun way and to do the same thing that we would have done essentially here. In fact, more challenging, particularly because of terrain. So this is kind of a flat surface, if you think of it, right? Also, this is Arizona, part of Arizona where all the Tucson has a lot of relief features. This part is very flat. So you don't have to worry about, you kind of take off, let's say you take off from start. You could do a lot of things just by making that assumption that your ground is flat. Now here, as you can see, this kind of a relief the relief structure, first of all, it's huge. So Mars itself is 1/3 the size of Earth, I believe. Even the gravity is roughly 1/3. But look at the scale bar here, 0 to 200 kilometers, right? So the thought is as more and more high resolution images have been coming, there were 3 candidate sites, out of which they picked the Zero crater, I think, fall last year. I believe that's when the announcement was made for where it will actually go, the Mars 2020 mission, the rover. And of course, the rover has a drone as well, but this time the drone will be more for kind of scoping out what they can do. But like, NASA might add some other goals. I don't believe the drone is carrying any instrumentation beyond some cameras. But this basin is huge, probably, I don't know, 600 kilometers diameter, right? But within that, there is a region where the event will happen. Actually, I should have had another image of the Zero crater itself, which you will see soon. But this is kind of a section of the crater, which is here, right here. And the reason it's of interest and why they're sending it here is they believe there was a river delta. In fact, these features you can see now. And so if you were looking for life, for example, on Mars, for signs of life, this would be a good place to see. Also, like, notice there are a whole bunch of craters. So this particular arena is about 45-kilometer diameter. So this, in fact, this whole region somewhere here is 45-kilometer diameter, like that, the region that we are looking at within this Ice-Sirius basin. Now, within that, there are craters of various sizes, which also brings up interesting questions on rover navigation. So we happen to have another project on mapping every single crater that you can, using deep neural networks and guided by human annotation to train the models. So there's a bunch of research questions can be addressed in this site and with good Earth analogs. Or you could kind of look at it the other way. We originally started with an Earth-oriented mission. Now we're looking at space analogs. So however you look at it, so here there's a nice image of that region. So the coloration here is based on geologists having, and then there is like a legend somewhere else on the internet, but the geologists kind of characterizing the nature of the soil. So this is false color. Mars, of course, kind of looks reddish mostly, but like, here they're painted with the kind of, like, I believe they have like carbonates and different kind of soils. And don't quote me on this. I'm just pointing out that the coloration shows the nature of the soil. But as for our goals, we are looking at kind of splitting it into a two-phase event with the qualifying phase that's going on right now, just to kind of get people on board, right? So those who have taken my coursework, there won't be any problem. Again, the goal of the qualifying is not to filter teams out unless, let's say, we are 100 teams trying to do, which might soon happen, but not right now, right? We want to kind of make it a rolling event. So once these 2 phases end, March 2020 mission will happen starting mid-July if everything goes well. The launch should be around that time. So potentially we can have another round where we keep the winners or the top teams or every team who has participated, they're kind of scoring, timing, and assuming they're willing, we would really like teams to keep their code on GitHub and for people to see, because what's the point otherwise kind of for this event. But we can have another round of 2 phases where people can try to beat their own scores, or other teams from around the world or wherever can give it a shot. But the main idea is qualifying. You get familiar with the PX4 stack, velocity, position control, visual surveying, bunch of things that we have discussed in our course, spring course. And I'll actually start putting some papers and material from that course to this event so that people can refer to it. Phase 1, the idea is you kind of get introduced to terrain relative navigation. The terrain relative navigation, or TRN as they call it within the NASA world, is actually being used for the lander, but the definition there is a little different. There they are still doing navigation relative to some terrain, but there the idea is to get the lander to a specific error ellipse. In our case, it's still moving relative to a terrain, but let's say you're doing what the lander would have done, but it's not so much just about reaching a certain region and staying there, but also about as you're moving, can you maintain some safe distance to terrain? So that would be more applicable for the drone for the Mars mission, which is using a very sophisticated flight controller. It's similar to PX4 made by Qualcomm, as far as I understand, Snapdragon Flight Pro. So it has FPGAs and it does visual inertial odometry. So it can, so terrain relative navigation, whichever of the 2 definitions you look at, the general idea is being aware of terrain and doing things related to that. The goals could be having a lander show up in a small error ellipse, or having a drone fly while not hitting terrain. So we have kept the qualification round goals simple. We'll see if people can finish by today. If not, we'll let teams kind of gently get into phase 1. It's not mandatory that phase 1 has to begin tomorrow, because UPenn just joined yesterday. So we can give it a few more days before we begin phase 1. But qualifying the goal is in the environment that you have with minimalist sensing. So right now the drone only has a down camera. So with the down camera and a probe whose color we had made red, but Mohammed was asking yesterday, can we change the color? I think that's fine. I can understand that the Martian orange probably has a lot of, the red is high, but like, remember, color is generally a tricky thing to use, but qualifying it's fine, because even if you detect the probe, you still have to servo and bring the drone within a certain cylindrical error. So the way Harish wrote the docking logic is to match our electropermanent magnet. So you can imagine that above the probe, there is a cylinder that extends up to like 50 centimeter, roughly speaking. And if the drone's base link comes within that, then it can dock, which is to say that if you had a small 15 centimeter cable dangling from under the drone with the electropermanent magnet underneath, if it mates with the ferrous top disk of the probe, it's connected. So we have kind of emulated that logic. So you have to pick up the probe and move it to this location that we have given. I mean, if you do that, again, of course, you have to use the camera. It's still a very complex challenge. In fact, many of the projects in our course in spring was pretty much looking at this problem, including Mohammed. But now you have to kind of do it in a place where there is terrain. And this, of course, you guys have seen. I'll mute the audio. You guys cannot hear the audio for this, right?
No, I couldn't.
Okay, I'll just talk it over. So let me mute. Except I can't hear myself now. Hang on, mute. So this is where the magnet is. And you can imagine that there is a cylinder going up above this, about 15 centimeter. So if the drone's base link comes within that, then in our gazebo will we mate it. Of course, this particular hardware, which we have GrabCAD designs, I believe Darwin has access to this, but you guys can make this at your own home. But the main idea is it has a Google Coral, it has a soil moisture sensor, but think of it as a template for a probe, just the same way we think of CubeSat 1U, 2U, 3U, like, you know, you could put different kinds of sensors, but at least you need some onboard compute. Doesn't have to be a Google Coral. Now, Google Coral is a tensor processing unit, so it can do the image processing with that camera that's there. The camera can be pointing sideways or down. So whatever you do, and it has like an environmental sensor. Now imagine whether this is on Earth or Mars, it has to be moved around, and there may not be just one probe, there can be multiple probes. So that's why we are doing this. And then we have come up with some rules which are fairly straightforward, but my hope is that teams will kind of engage and chat with us, and we'll all figure out what's a decent set of rules where we don't constrain ourselves so much that we are not doing research anymore. We are just trying to beat some metrics. And at the same time, we want some constraints so that we are making progress and we can measure ourselves. But for qualifying and hopefully even for the later rounds, we probably won't allow deep neural networks. I mean, the reasons are, I mean, we might. We have to just figure out how to train the models and everything. Maybe it's fine and maybe it is realistic. The main challenge is GPUs in space are still not a thing. I mean, Mars surface won't have as much radiation as, let's say, on the in space itself, or on moon where there is zero atmosphere. But in general, GPUs, space application, it remains to be seen. FPGAs, yes, but those are kind of the things that are running on the sensor. So to the extent possible, we would like to see how much you can do without DNNs, but we might allow if all teams feel that, why not? We just need to make sure that our servers are also kind of not getting all bogged down because someone wants to train their model and for 10 hours or 7 hours or 2 hours, like one GPU is at 100%. We want to avoid those things and use those compute cycles rather on some other thing. But we can talk and Harish can guide us on that as this thing goes. And as for scoring, we want to set things up so that we can do many trials. Essentially, just imagine we take your code and spawn 10 containers in parallel, each with slightly different initial condition, and we let those 10 simulations continue, and we then take all the 10 containers and kind of average some metrics, such as how often did you succeed in the mission, whichever phase we are looking at, or let's say for each. The qualifying is more to kind of get your hands dirty. So we'll try and do this for qualifying maybe, but especially for phase 1 and phase 2. And these are the kind of things we'll put on a scoreboard, and it will remain on that site for those who do well. But this is important. We want to make sure that we have some measure of multiple dimensions, such as success rate, total mission time, efficiency. And some of these, if you change your initial conditions, you have to do it multiple times to get a sense. And while doing this, we'll also learn when we write papers, let's say, what are some good ways to showcase how well you are doing. So yeah, that's pretty much from me for today. So if you have any questions, I can take it. I have been making a lot of updates to the containers. So anyone new, anytime they join the stack, they probably see the latest. But some of you, as you saw, there were questions on Sonar, which I then fixed. So any new container will have the correct one. So I'm progressively making those changes. Also spread the news among your friends. If someone's looking for something to do, they can use this opportunity to learn, something cool and stay engaged, have some, and then their code will be online. They'll get some visibility and publicity. All right, questions. And I want to show you some, how the phase 1 world will look like, etc. So let's then go ahead and let me show you what the phase 1 goal might look like. One thing I would point out, there are some tricks. So you can see my screen now. So typically what I do is I just hit somewhere on the left after it has started, and I right click on this, and then I open it on a new tab. So that way I get a full screen. And then I don't do this on the Mac often, but when I'm working on my Linux, because on the Mac, the keys, I don't work on my MacBook that often. Usually I'm on a Linux machine, but you can make the browser full screen, and then the experience is very nice. You'll forget that you're actually working on a browser. You can also make it full screen here, there is a no VNC tab, but then if you hit escape, it will again stop being full screen. So right now it's full screen, but if I need to hit escape for something, then it kind of goes out. But if you use the browser's full screen behavior, somewhere here, then it's a little better. I don't know how much of this you can see through Zoom, but things are happening at my end, but so that's fine. And then the other thing I can do, and at this point I'll actually switch to my Linux machine. Oops, 1 second. I have a better keyboard on my. So okay, I'm here. And again, I use my command and left arrow, Control Shift O to split the screen, etc. So let me just directly show you the phase 1 arena, because we can, or actually why phase? Let's start with the qualification thing, right? Let's kind of just do a full run. So this is our package, CPS Challenge. So you will notice that, in fact, another thing I do is I pretty much exclusively use PyCharm for my stuff. In PyCharm, there is also a terminal, but like, you know, there are some, I was trying, you can use the terminal for some other various things, but you might still need this terminal behind the scenes. The resolution is interesting. So let me actually reload this. Okay, better. All right, so now the world has started. No big deal, like, you know, there is a probe here. Harish has written some logic where the drone, if it shows up right above these red cylinder, I have fixed the inertia as well a little bit. Still, like, you know, you have to make sure that you drop the probe so that it doesn't start rolling and goes somewhere else. We will, the objective is to ensure that you drop the probe very close to where you originally intended to drop it, which means that you can't just drop it from 20 meters above. Then it will land up somewhere, and we can easily measure where the probe showed up, because we can read every link's state in, like, you know, using Gazebo, for example, actually using Gazebo, that's how you'll do it. So let's put this to the right. Next thing I'll do is I'll start this Gazebo link attacher, which is where Harish has modified the logic so that the attachment happens only when the drone is within a certain cylinder of acceptance. It's actually like a tapered cylinder. So the base is a little narrower, almost like a cone, but a cone kind of tapers to a point. Here it doesn't taper to a point. It tapers to kind of, I forget, 10 centimeters, I believe.
JD,
Goes
it's
from
not
15 to 10 or something like that. It should be there in the code itself.
Yeah,
so now the probe is activated. You can think of it like that. It has been armed. So if the drone shows up, it will attach. Of course, in reality, it will happen directly through the magnet. But you can imagine that if you had an active docking mechanism, let's say you're in space and some spacecraft is about to dock, and if the spacecraft is making the decision when to engage the latches, so that's one way to think of it. So that attach is kind of enabling that. And the third thing I'll do is I'll run the docking code, which will, so by the way, look, notice that I am hardly typing anything. I'm just using Control-R, reverse history search, and pulling up the commands. There are some ways you can be efficient. So this is not using visual servoing. I'll pull up RQT, but you have the down camera data and you also have the sonar data. And the sonar, I apologize, I had been a little sloppy with that. I had not checked it before I made some change. I kind of just took it from our old drone and never bothered to check it. So now it's working. Now the probe has been dropped. As you can see, I dropped it from some height and it didn't, now it's rolling around. So now your accuracy is less. Of course, it wouldn't roll as much on Martian soil. The elasticity that we have set, the stiffness, it's like the ground is a little more elastic than it should be, which is fine. I think computation is that. But you can see that this is a kind of deployment where you have some error, right? Even if it goes on doing this for a while. So ideally, you would want to kind of find that sweet spot where your probe doesn't tilt over. And also don't change the size of the probe. If you do that, we have to make sure other teams get the same setting. So some things we would like to keep constant within the team. So the properties of the probe will make sure that when we run our tests, and at least in your containers, I can always go behind the scenes and make sure the inertias are all the same, and etc. So that's that RQT. Where did it go? So you can kind of see maybe the probe rolling around on the ground. Any questions so far? Cool. So let's show you the, so this is probably useful. Now I can, yesterday I was trying a thing where, you know, in fact, let me show you. So I can do this mission again. Let me just kill everything. Let's bring in
Professor,
Q-ground
I have a
control.
question.
So I also usually have Q-ground control open because that allows me to do various things on the side, like imagine new scenarios. Oh, I have to start the simulation again. So let's restart it. Let's put Q-ground control to the right. So again, I used command and right arrow to put it there. This time what I'll do is once the probe attaches, I'll stop the docking script so that it doesn't drop it after 15 seconds or so like it does. And instead I'll try to take it to the top and drop it here. And in fact, that's the goal of the phase 1 scenario where you have to not deal with this terrain. Of course, in phase 1 or in phase 2, this will be embedded in the Martian world. And that's the whole Mars scene. You can kind of see the scale of that terrain. But let me show you that piece. So now I have Q ground control for that reason. I'll also enable the virtual joystick. And Harish, I saw you earlier. One thing we need to figure out is to ensure Q ground control settings are safe, because it's running from the user account, but it's being run in the root account. So I think when Q ground control closes, where it's trying to save its settings, it's not readable the next time it starts. So it must be a simple kind of a symbolic link or something that we need to create so that, for example, these thumbsticks should show up every single time I start. Right now, every single time I have to kind of enable it because it's not saving its last setting. All right, so let's do that again. And this will be kind of me showing you a teaser of the second phase goal, but the second phase also has a rover, and the third phase, sorry, the first phase goal, and first phase and second phase involve rovers. So let's enable the attach. Let's start docking demo. Let's put it to the left. Now I need to make sure the moment the docking has happened, I have killed the okay, am I running it? There we go. Okay, and now Q ground control engage is fail safe, but I'll override it, put it in hold mode. Oh no, change altitude. If I can do it fast enough, then the drone won't become unstable. Like the moment its state estimator goes a little funky, you can no longer use that. There we go. Managed to save it. Did we? Yes. No, maybe not. What happened is it was too close to the ground when I attempted. All right, this this demo failed. So let me just show you the first phase environment, how it will look. Any questions? I'm kind of just goofing around, I guess. Nope. All right, so the final demo for today will be me not running this, but using this other file called Bishop, which is the California volcanic turbulence world. Z0 is that crater world in Mars. And now you will see there'll be a drone and a rover. Both actually are active PX4 devices. So that this is where you're now going to kind of to the next level, where you're no longer talking to just one entity. There are two entities. For phase 1, you don't have to, in fact, for this challenge, we are not making you deal with the rover at all. So we'll just make the rover for phase 2 kind of move at a constant speed. And your goal for phase 2, and that's why it's challenging, should be to, so there you can see this vehicle now. In fact, this vehicle, I can make it move, and I'll show you the evidence of that by splitting the screen. And I'll use the raw topic pub. UAV 0 is now the rover. So let's make the screen left. And set point velocity, command velocity unstamped, etc., etc. Rest. So everything pretty much remains the same. And recall that the way the rover is pointed now is actually positive X. Left is positive Y. So right will be negative Y. So I'll just add some negative Y, right velocity. And let's put it like 40 centimeters per second, negative. And that will be published at 10 Hertz. And the moment I switch to off-board, and here also you'll notice that there are now two vehicles, vehicle 1, vehicle 2. Now you have to remember that here vehicle 1 is rover. That you will know based on your launch file, the sequence. That's where we have the ID, which is all in the CPS Challenge Catkin workspace folder. That's where Harish has nicely organized all the files relevant to this challenge and kind of our ecosystem of like the kind of things we are doing. All right, so what are we getting at here? I will just simply switch it to off-board mode and arm it, and it should start going right to the right. So imagine if this vehicle is doing its thing, it might eventually hit a rock because it's not doing obstacle avoidance. So I'll just disarm it. So imagine if this vehicle was just moving constantly. Now your drone has to do some stuff and then eventually come back and land on the moving rover. So that's the phase 2 goals. Of course, now I can also take off the drone and you will start seeing the, I don't remember if in this world the drone has a camera or not. Well, it should have ideally. So I can now take off the drone as well, take it to like, and in fact, it will be fun if the rover gets stuck on a rock, because that essentially shows that you have to, will allow you to access the location of the rover. But if the rover is moving and doing its thing, or if there is a state estimator error like this, then you might still have to do a visual search. So let me actually just disarm the rover, because it's trying to move its wheels and it's not trying to stop itself, and hence its states are, so till we disarm, it will keep doing that. But once we disarm, its state estimator will slowly converge to its current location. But that location will be available to your drone. And where did my drone go? It has taken off now, yeah, somewhere in the air. Where is it? There we go. So you are essentially in kind of the phase 2 scenario, except this rock world will be in the Mars terrain, and this terrain is actually here. I can show you. Bishop terrain, where is the 0? Do I have the terrain here? We have the Mars terrain somewhere. We can load and show you. Yeah, there we go, the 0 crater. Now, I don't know where the terrain will show up. So now this whole world is actually in a Martian terrain. Of course, since I kind of dynamically inserted it, it went a little crazy. You can kind of see the scale of this world. Let's change the color to a little bit viewable. So that's the Martian terrain on which now we kind of inserted our bishop world, poorly, because I kind of did it dynamically. Ideally, I'll move it, up a little bit. So we have a world that's saved, and I have carefully found a little location within the Martian terrain where the bishop world fits very nicely. And that's kind of the idea of the last phase, of course, with not we have a proper world with proper lighting and embedded instead of how I showed it here. So the fact that this is living in the Martian world, it's important because we might try, once this 10-15 day event is over, we might try some things in the Martian terrain itself, not just in the bishop terrain, such as, let me just change the angle of the sun for a second so that there's nice shadowing. Rotate. Sun. There we go. So now if I zoom out, you can kind of see the features a little better. This world is kind of hanging here. But if I zoom out, this is going to be that same world that I was showing you in your slide deck, the river delta, etc. Hopefully you can get an idea. So what are some things you begin to see? You can kind of see the scale of this event as area, right? So it's a big area, and the rover is tasked to land within a, I forget, Harish, if you remember, let me know. I think it's a 10-kilometer region. So this is a 45-kilometer region, this whole curve. You can't see my arrow, but kind of imagine. So this is like a channel, the river channel. This is the delta. So imagine if you had to fly a drone on an airplane through this canyon, right? So, and then deploy a probe somewhere here. I am thinking that we will leverage the buzz that will be generated for the July 2020 launch and try some very cool stuff, assuming that we can solve the first 2 phases that we have kind of planned. So then we can make it a recurring event for the first 2 phases and try some other things here. But hopefully you can, at this point, you get the idea why we're adding a earth terrain, which is a volcanic, a tectonic fault scarp, bishop. So in Mars, I guess the answer is why not, but there are other interesting things that manifest from us doing that. All right, ladies and gentlemen, I think that's all I had for today. So let's kind of take some questions, and we can do webinars as often as we need to. Just unmute yourself and start talking.
Is the state estimation part done by the PX4?
Right. If there are
modules?
no questions, let's make sure there are no questions. Where is the chat window?
Someone was talking.
Oh no, there are questions. Sorry guys, I did not see oh yeah, Mohammed and Harish. It's six. So Harish points out it's 60 centimeters above and 30. So we are actually like, keeping it a little less taxing than it normally is. Like, normally it should be 10 or 15, but this is good. And Mohammed, can you ask your questions, or is it something you didn't want everyone to know?
Can you hear me now?
Oh, wait, I am muted. Is it? Oh, sorry guys. Was anyone talking earlier? Because when I was earlier watching that video, I muted myself. And which means that anything you guys were saying, I didn't hear. I completely apologize. Yeah.
Yeah, I think a couple of people were talking.
Okay. Anyway, that has passed. I'll have to re-watch kind of the recording, and there I might. Sorry about that. So yeah, can someone again mention what others were talking about earlier that I might have missed? All right, Mohammed, go ahead, ask your question. I think you were trying to talk earlier when I was muted, like at my end. My audio was muted at my end.
Okay. Yeah, actually, I joined a couple of minutes late. So just to make myself clear, I wanted to know I want to make sure that I got the rules properly. So once for the qualifying round, we will launch the drone, and the drone should look for the probe and pick up the probe and go to that location. And then once it goes to that location X, Y, it should drop the probe there and go back to some other location, right?
Sorry, can you repeat that? So the drone takes off, it picks up the probe. So you have to first find the probe.
Yeah.
And in fact, the probe, you know where it is. So it's not like you have to, it's just that you shouldn't hard code it. You should begin a lawnmower search. And of course, you will see it very quickly. Yeah. And then you servo, you pick it up and then continue. What were you saying?
Yeah, so we pick it up and then we place it at this 25, minus 35 location, right?
Yeah, without hitting the terrain. But like, in this case, you don't have to worry about the terrain, where the location is still kind of in the flat region. Yeah. And drop it such that it doesn't keep rolling. So you have to make sure it's not being dropped from a height where, it's going to roll away, but that's less of a concern. If you can just show that, you can just do the whole thing, then it's fine. Having said that, like, we'll see how people onboard. So as of today, PEN kind of just started yesterday. So I think you still have some time. We won't begin phase one unless at least 2 teams have showed a proof of concept. And once they have, we'll begin phase one. But those who are still kind of catching up, they can start the phase one thing when they're ready.
And once you drop it at 25, minus 35, the drone goes back to the start location?
Once you drop it, that point, the qualifying is over. You can just complete things off and kind of just return to land, essentially.
Okay.
I mean, you can literally just engage the return to land command, but for qualifying, it's fine. If you're on that Martian terrain, also it's fine. But remember that in Martian terrain, there is no concept of flat ground anymore. Basically, you have something that's not flat ground in something that's not flat ground. But at least in the Bishop terrain, there is some sense of flatness right here. Like this is quite flat. So we are keeping you in this easy arena first, and then all hell will break loose soon. And so I should point out that for the second phase, the probe will be have to be dropped somewhere on this top part. Because if you think about it, those are the kind of scenarios. So why are they sending why is there a drone with the rover? I mean, it's so quite obvious, right? You have eye in the sky, and the phrase they use is forward reconnaissance. So the drone can kind of help guide how the rover should move or do these kind of tasks, like, deploy probes or do caching, get a sample from somewhere. All that won't happen when the current Mars 2020 mission reaches, which is coming February, because this drone is more like an engineering demonstration. But you guys should read about the drone, the Mars helicopter, Mars Heli. It's very sophisticated, big rotors. So some of the other things that will be of interest for you all is just the dynamics of the rotor, etc. But anyway, Mohammed, carry on. Any other question on the qualifying?
No, I think this was pretty much it.
Yeah, just don't change the size of the probe. Otherwise, you can change the texture and other things however you want. You can even put an April tag on top or something. It's just that you can't see it from high altitude. So just basically going by what you are doing is fine. Like, looking at kind of a contrasting surface that has, of course, you can, once you're kind of close, you can deliver as the circle. You
Correct.
can put a dot at the center. Those are all fine. But the reason it's okay is because if you're designing a probe, to the extent you can, you will put fiducials and kind of structure it in a certain way. In fact, most things that go to space have fiducials all over. Now, of course, if we had put constraints that, look, you can't put anything on the side of the probe, then every team will have to do that. We are not doing such thing. This is, as far as you're considered, as far as this event is considered, it's a cylinder, that's all. And you can do whatever you want to it without changing the size or the inertia and mass.
Okay.
And the inertia I'll actually update for some of the older containers. Right now, the inertia is a little wider, so you'll see the probe kind of tipping back and forth as if it's a very wide object for some of the older containers. So I'll just kind of update those. And again, any other commentary that I missed earlier because I couldn't hear you all, and I'm feeling kind of silly now. So just can you repeat that? If you asked something and I just kind of kept up talking, that's because I didn't hear you.
I had a question on how the state estimation happens. So does all of that
on
happen
for the drones?
on the drone? Yeah. Is it taken care of by the PX4 stack, or is there some way we can access it and take a look at how those things are implemented?
Yes, the PX4 stat has a state estimator, and you can. So this is, in fact, there is a paper, this particular paper itself. So you can see this is kind of the layout of the PX4 stack, and where the state estimator is accessible. So now I have two vehicles, and they have their own identity. So first place you can see is that on the. Oops, 1 second. I don't know why there's a. Let me just start the original scene of the one drone, not this world. So the topic is Mavros, local position odom, that's the odometry topic, and also pose, one of which has the covariance and the other doesn't. So it's running an extended Kalman filter where they're integrating the gyro, using the accelerometer as the process model.
Okay.
Fusing GPS. So yeah, there isn't a dynamical model. They're just using the accelerometer data. And then there are a bunch of stacked controllers, and I'll actually share this. I presented this, I think, in the class, but these are the stacked controllers. So you have a body rate, so attitude rate and attitude. Attitude rate is, again, this is the number that I think it's 500 hertz, the attitude rate, and the attitude controller is 100, and then position control, and there is a velocity controller as well. So from the position controller onwards, it has a state estimator that's leveraged. Under this, it doesn't need to be aware of a world frame. Now let me show you let me show you all of this you have access to. Oops.
So to actually see how this works, is there a way we can take a look at the source code or something? I mean, I know it's not necessary for the challenge. I was just interested in.
Yes, Google might help you.
Okay. Basically the PX4 stack, right?
Yes, px4.io.
Okay.
And this paper, this is from a paper, so you can read that. I mean, look, I can also tell you, but I may not be the best source to explain when there is already so much available online. Now, I'll just show you where to look these things up. But the paper will be the best place to see.
Okay. Yeah.
But px4.io and dev.px4.io, and it's a huge community. So I'll do them an injustice if I don't point you to that and try to do this myself. But look at, just kind of spend some time. And there is a virtual summit coming. It's free. I registered on Saturday, July 6th and 7th. So in fact, all of this will kind of prepare you to see all the kinds of things you can do. And the kind of things you can do are kind of vehicle layout agnostic. So you can see that there are VTOL, vertical takeoff, quad rotors, rovers. You can see we are making underwater. So it just gives you a lot of power. So let me get back to the page and show you the state estimates. But Mavros is the other thing you can look at. If you want to just keep your life simple, the thing you should focus on is the communication protocol, which is Mavlink. And in fact, Mavros is what we use. So whatever Mavros allows, you can. In fact, this should be, so if you get to local position, these are where the state estimate topics are coming, but estimator topics are coming, but you have to kind of go into these things or see if someone else has written. Right, now, the other part that you were asking, the source code. Yes, so go to GitHub. Oops. PX4, I think github.org, PS4. Of course, that will have hardware and firmware. Sorry, I shouldn't have. Let's just do again. Hardware, I am sometimes concerned with. For right now, whatever we are doing, we are least concerned about hardware. We know of the hardware aspect as it. Those of you who have, like Darwin has a flight controller that I gave him. So he might see the hardware part, but actually let's go one level lower. Why didn't the PX4 thing load earlier? Is it case sensitive, the names? That's weird though. So you can see
Yeah, I
this
think
is kind of
URLs are case
the,
sensitive.
got it. So it has a whole bunch of things, but your concern will only be with this. Now the state estimator is actually implemented in, I think, source modules. Let's see, where are the modules? Let's do a search. One sec, let me do a search like the modules, or we can also do it on our, that same source code actually exists on your container. So the idea is that whatever we do, we can literally do a firmware build and put it on the hardware. That's kind of the idea. Let me move this annoying zoom bar. Okay, so let's go here and I'll show you what I'm talking about. So in this folder, you can see source firmware, right? That's what the GitHub repo maps to.
Oh, okay. Yeah.
Within
I think I'll
that,
be
so
able
this is
to
actually a direct
find it.
mirror image of, and it takes time to actually get this build toolchain to get reinstalled. What you are getting access to right now in the container is actually a massive time sink if you try to do on your own, getting the whole thing to work and then keeping it up to date. So we have simplified that part for you. And then there are a lot of details like, this has aspects of what's actually running on the flight controller, as in the Iris drone that we use. Let me just go down a little bit. This is the equivalent of what the, okay, not, that was a little anticlimactic, but it's quad W, hang on. Anyway, we can also open this one. This is reflecting what the flight controller internally is setting. So not on the actual hardware of the flight controller, on the micro SD card or the file system that it has on board. These are all this will look kind of familiar, right? This is the multi-copter pitch, proportional gain, etc., etc. The kind of things that I can also change, in fact, from Q ground control. So this is also using MAV range. And so it's a pretty huge arena, and it will take you some time to kind of get familiar, but as you poke around, you'll see that, so the whole thing is open source, of course, right? But that means that there's a lot of information, a lot of things you can change, but you won't have to change all of that all the time. So kind of to get it back and show you the state estimate, which you can see it here, you can also see it in Arviz. So literally, in fact, what I'll do now is I will, once this thing starts, I'll just pop up an Arviz and show you the pose as an arrow. So this is, of course, Gazebo. Gazebo is not needed. I usually keep Gazebo open because now that we have massive servers, it's like, it doesn't really affect the performance. But if I'm working on my, even my 8-core VR little desktop that I have, like if I have Gazebo, that bunch of things running and 2 drones, then it starts struggling. All right, so I have the Gazebo world. Now what I'll do is I'll pull up Arviz, which so far I haven't bothered to show. In fact, once you get into some serious experimentation, you might have to set up Arviz the way you want to scale up. Otherwise, life will become a little nightmarish. So it's maybe not a bad idea to look at Arviz right now, for those of you who haven't. And as for the state estimator itself, let's put Arviz to the left. As for the state estimator, this is actually the real-time operating system terminal. So the PIXOC runs NUTX, which is a real-time operating system. So hence, I sleep well at night knowing that the flight controller has like very good guarantees on latencies and other things. But like if I do, even if I simply do help, you'll see that there will be an EKF2 somewhere listed here. Because right now I'm actually literally at the flight controller level. Normally, when you're flying the drone in the real world, you wouldn't be kind of logging into the flight controller and doing this. Instead, you'll be using MAVLink or Q ground control. But since I have on this, I can do EKF2 status, and it's showing that it's running. If I stop the state estimator now, you'll actually see that in the software in the loop setup, it will actually crash the simulation. In the actual hardware, if you had the PIXOC, you can actually stop the state estimator and restart it, especially when it goes really crazy, your estimates and other things, and you're like, oh, you know what, it's time to restart the state estimator. But why didn't it connect? Let's close this. Let's just start Q ground. Actually, no, we don't need Q ground control. First, I'll show you the pose messages here. I don't know. Oh, that's always. So through Mavros, so I'll do ROS topic, echo. Now that I'm running the fast simulation, there's only one vehicle, so I don't have to do UAV1 and all that. Hold on. That's coming from the state estimator. Now there is also pose, so you guys should poke around and inform me where the covariances come out properly. Because this is a software in the loop setup, the covariances in simulation, you might have to specify it in one of the YAML files for PX4. And then you, so right now I think the state estimates have no noise, or maybe the variant covariance is not being published, but Harish, you can maybe just double check that piece. Like, for the EKF that's running on the PixArt, just some investigation into the covariances for it and how we can, like if you bump up the GPS noise in the SDF file, then kind of observing that the pose of the PixArt, I know that some of the teams leverage that for the projects, but I need to also take a look there. But let's get back to me showing you the pose. So you can see all the topics being published right now. One of them will be local position. So yeah, there is a pose covariance. Maybe that's the one. Let's actually try that. But let's first try the devil we know. So here's the drone. That's coming from the Kalman filter. Now, if I start, actually, I don't even have to start Q ground control. Momentarily, I can make it take off. Then the flight controller will realize it doesn't have an RC controller or a virtual joystick that we run on the Q ground control, it will land. And that's the state machine that it's very powerful. So it's aware of the fact that it doesn't have a ground control station or an RC transmitter. So it will land itself again. Happy, Rakshit?
Yeah. I think this is good overview. Yeah.
So use this competition as a way to kind of also understand the PX4 stack, and they have a Slack as well channel, and it will take you some time, but once you get a grasp of the basics, right? Like at least the things you need. So which means that I'll share that slide link again, and you should kind of look at this paper that, and you might, I don't know if you were in that class when I discussed this, but this paper is probably the best resource. And then, but this is old, I think this was like 2012 or something, I don't know. I don't recall exactly, 12 or 13, 15 maybe, 2015. But things haven't changed that much. Like, I mean, it's a big community. There are, I don't know, 35,000 commits or something on the GitHub repo, which is a great thing. And the same thing, right? They have a firmware and then they have a hardware where they have the details of all the hardware aspects. So you could, if you're good at making circuit boards, PCBs, you can literally make your own PixArt hardware, based on their designs. So. But I think the important bits are this slide, like how their controller stack is. And this, because this is showing on the flight controller, like this thing that I was on now, like this is the NUTX terminal. And it's essentially from there you can access, like, so you can kind of see which parts. So I can look at the sensor drivers, actuator drivers, all the stuff underneath. Then there are some things, actually all of these are running on the NUTX, the state estimator you saw. But then it uses a similar structure as ROS, this message broker, UART messages. So even within the PixArt, it's an asynchronous message passing. There's like a message broker. Do you need to understand all of these to do something interesting and, solve a problem in the world that you care about? Probably not, right? But,
no, it was just to get an overview of how a full-fledged stack is implemented.
Yeah. So that's a good way to put it. So the flight stack, right?
Yeah.
To get a good grasp, it might take you some time, but then you will come out of it being able to do a lot of things. And now that we have all these simulation environments, you can literally just test things out. And then the final piece that I was saying is, what's the time? 51. Okay, we have a few more minutes. I think the final thing, which I don't know when I'll be able to show you all, when I can maybe meet people in person, which is the piece that I want to take, especially those who are around in fall. If I go to source, firmware, of course, you guys are using the CPS challenge, kind of like, this is how we were launching our code, right? But you can also go to source firmware. And in fact, inside this, I can do a make. There are various targets. We have done all of this. One of those targets are make, I think let's call it PX4 FMU V5. I have to look that up. And then that makes the flight controller it cross-compiles it for the ARM Cortex, and then you can do an upload, and it uses the serial link and uploads the firmware that you have just built to the PX4. Why do you need it? Well, it's useful if you want to go and change the flight controller code. And yeah, modules. So if you go to modules, I think I was trying to, there you go, Rakshit. You can see where all the code is. So you might then go and change, I don't know, whatever you want. So like you are into EKFs and other things. So you might be interested in the multi-copter, or actually, let's go away from the EKF. Let's talk about the attitude controller. So you say, I want to change the attitude controller code. So fine, you change it, you test it in simulation. Once you're happy and you have done hundreds of tests and simulations, and then you can reflash your flight controller.
Yeah, okay, yeah.
And this is just one piece I'm talking about, right? There are various other things, including the state estimator and all that. Yeah. So Navigator, for example, is the highest level controller. And this is what the 95% of the world uses for most flight controller, which is the mission planner. Which is working at the GPS level. In our world, that's something we do only at 10% of the time, or like to do only 10%, because the rest of the time we're running a tighter control loop, which is like position control or velocity, or even lower attitude control or attitude rate.
Yeah.
All right. Anything else? Anyone? And I'll share this recording, feeling a little silly that I have muted myself. All right, so on that note, let's maybe call it a day, and then we can have another webinar in a couple of days when we'll see how people are doing at qualifying. I don't want to make your life stressful, so just keep me posted how things are going. If people need more time, we can roll the competition a little longer. The whole idea is we want to kind of have one more of this after this phase 1, phase 2 is over, leading up to the July launch of the March 2020. And then another thought I have is that if we come up with some good work, we can write some ICRA papers, showcase both the research end of things. And then I know that some of us have plans of writing a paper around the tool chains, and those who contribute and come up with good solutions, we can kind of discuss, putting people as co-authors, etc. So there are multiple things we can be doing. All right, thanks everyone. If there aren't any other questions, I will probably adjourn this meeting. All right, bye.